Welcome aboard, space crew. Today's mission takes us deep into the mysteries of the universe. So hold on tight as we blast off into the stars.
Are you sure the universe works the way you think it does? Astronomy has rewritten its own rules again and again, demolishing certainty with every new observation. So, today, we're counting down 15 mind-blowing space facts that turned astronomy upside down. 15. The sun is average. For most of human history, the sun felt untouchably special. It lit our skies and shaped mythology across civilizations. It seemed impossible that something so central to existence could be ordinary. So, what if the star that defines our world isn't special at all? By the early 20th century, when scientists began classifying stars using the Hertzsprung-Russell diagram, something uncomfortable became clear. Our sun isn't a cosmic giant. It's a G-type main-sequence star, a yellow dwarf, sitting almost exactly in the middle of the stellar spectrum. Not the hottest, brightest, or most massive. In fact, roughly 90% of stars in the Milky Way are smaller and dimmer red dwarfs, and many are far more dramatic than ours. And worse? Its chemical makeup isn't rare either. It's what astronomers call a population 1 star. That discovery did something subtle but profound. If our star isn't special, then maybe our planetary system isn't either. And if stars like ours are common, what else might be? 14. Planets are common. There was a time when the word planet meant one thing: the handful wandering across our own sky, Mercury, Venus, and Mars. That was the entire known inventory of worlds. By the 1990s, one question lingered. Were planets rare cosmic accidents or common outcomes of star formation? In 1995, astronomers found the answer orbiting a sun-like star 50 light-years away. It was 51 Pegasi b. Since then, missions like Kepler and TESS have revealed thousands of exoplanets, and statistical models suggest they're not rare exceptions, but a rule. Now, current estimates indicate most stars host at least one planet. With roughly 100 to 400 billion stars in the Milky Way alone, that implies hundreds of billions of planets in just our galaxy. Expand that across trillions of galaxies and the numbers become almost absurd. Many scientists now estimate there may be more planets in the universe than grains of sand on Earth. Like hot Jupiters, super-Earths, ocean worlds, and rogue planets drifting without stars. So, Earth didn't lose its beauty. It lost its exclusivity. 13. Galaxies frequently collide. From Earth, galaxies look eternal. Vast spiral islands of stars drifting silently through the dark, too enormous and too distant to ever truly interact. For decades, astronomers even assumed they evolved mostly in isolation. But what if I said they don't? That's right. Galactic collisions are not rare accidents. They're a fundamental part of cosmic evolution. When Edwin Hubble confirmed that galaxies exist beyond the Milky Way, it opened the door to an even bigger realization that the universe is crowded. Over time, gravity pulls galaxies together, and they merge. Our own Milky Way is on a confirmed collision course with the Andromeda Galaxy. In about 4 to 5 billion years, the two spirals will begin to interact. Their shapes will distort, gas clouds will compress, triggering waves of new star formation. Eventually, they'll settle into a single, larger, elliptical galaxy. Despite the drama, individual stars rarely collide, because space inside galaxies is mostly empty. But their structures? Completely reshaped. Galaxies aren't permanent monuments. They grow by consuming and combining. And if collisions are normal, then maybe even our own galaxy isn't as stable or as unique as we once believed. 12. The Milky Way is ordinary. When astronomers first realized we live inside a galaxy, it was staggering. The Milky Way suddenly became this colossal, star-filled system stretching over 100,000 light-years across. It felt enormous, unique. But what happens when you discover there are not just a few galaxies, but trillions? As telescopes improved, especially deep-field observations from Hubble, scientists began counting galaxies across tiny patches of sky, The numbers literally exploded. Now they say the universe may contain up to 2 trillion galaxies, and when researchers compare their sizes, structures, and star populations, the Milky Way doesn't stand out. It's a fairly typical barred spiral galaxy with an average-sized central black hole and a standard rate of star formation. It's not unusually massive or architecturally rare. Cosmically speaking, we don't live in a galactic capital. If our galaxy isn't special, and galaxies themselves aren't rare, then the scale of ordinary is about to get much, much larger. 11. Black holes are common. For decades, black holes were treated as exotic possibilities. Then, astronomers tracked stars near the centers of galaxies and saw something impossible. They were orbiting an unseen mass, compact, invisible, and far too dense to be anything ordinary. Now, how could something invisible exert that much gravity? Well, the conclusion was unavoidable. Most large galaxies, including our own Milky Way, host a supermassive black hole at their core. Ours is called Sagittarius A star, weighing about 4 million times the mass of the Sun. Beyond that, stellar mass black holes, formed from collapsing massive stars, are scattered throughout galaxies. Some estimates suggest there could be millions, even billions, in the Milky Way alone. And once gravity can trap light itself, the rules of space and time stop behaving the way we expect. 10. Gravity bends light. What if light, the fastest thing in the universe, doesn't actually travel in straight lines? For centuries, physics assumed it did. Like light moved forward, clean and predictable. Gravity pulled on mass, not beams of brightness crossing empty space. Then it changed. Albert Einstein proposed something radical in 1915, that gravity wasn't a force pulling objects through space, it was the curvature of space itself. Massive objects distort the fabric around them, and everything, even light, follows that curve. It sounded almost philosophical. Until 1919. During a total solar eclipse, astronomers measured starlight passing near the sun. The stars appeared slightly shifted from their normal positions. Their light had bent around the sun exactly as Einstein predicted. It confirmed that space wasn't rigid. It could warp, stretch, and curve. That single confirmation shattered classical physics and launched modern cosmology. Now, once space itself can bend, the idea of empty space becomes far more complicated than anyone expected. 9. Space is not empty. When you picture space, what do you see? A black vacuum, a perfect void, or absolute nothing? That assumption feels obvious, but it's also wrong. Even the darkest regions between galaxies aren't truly empty. Interstellar and intergalactic space contains sparse hydrogen atoms, stray radiation, magnetic fields, and high-energy particles traveling near light speed. On a quantum level, things get even stranger. According to quantum field theory, what we call vacuum isn't zero. It has baseline energy. Tiny quantum fluctuations constantly produce virtual particle pairs that appear and vanish in fractions of a second. The vacuum itself seethes with activity. Astronomers can even measure vacuum effects indirectly, such as through the Casimir effect and quantum corrections in particle physics. Empty space has structure. It has energy. It influences how the universe expands. Nothing turns out to be something just incredibly subtle. So, if space carries energy, then the universe may remember its past in ways we didn't expect. 8. Stars eventually die. We grow up wishing on them. Meteor showers streak across the sky, and we call them falling stars, making silent promises under something that feels eternal. For most of human history, the stars were symbols of permanence, fixed lights that never changed. But what if the sky itself has a lifespan? See, stars are not eternal flames. They are massive nuclear engines powered by fusion, converting hydrogen into helium deep in their cores. That fuel is finite. When it runs low, stability ends. Smaller stars swell into red giants and shed their outer layers before fading into white dwarfs. Massive stars die violently, exploding as supernovae and leaving behind neutron stars or black holes. Even our sun has an expiration date. In about 5 billion years, it will expand into a red giant large enough to engulf Mercury and Venus and even our Earth. So, yup, the night sky isn't permanent. And if the stars themselves aren't eternal, the idea that we sit at the center of something stable becomes harder to defend. 7. The Earth is not central. For centuries, Earth wasn't just home, it was the center. The sun, moon, planets, and stars were believed to orbit us in perfect celestial spheres. The cosmos felt designed with humanity at its focal point. That model held for centuries. Then, Nicholas Copernicus proposed something destabilizing, that Earth orbits the sun. Later observations confirmed it. Still, did that finally settle our place in the universe? It didn't. The sun turned out to be one ordinary star among hundreds of billions in the Milky Way. Modern cosmology goes further. On large scales, the universe has no preferred center at all. Expansion happens everywhere, uniformly. There is no cosmic spotlight, and humanity wasn't repositioned. It was decentered entirely. Once the universe lost its center, it also began to reveal something else, a measurable history written into space itself. 6. The universe has temperature. In 1965, 2 radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were troubleshooting persistent static in their antenna. The noise wouldn't go away. It came from every direction in the sky, day and night. It wasn't interference. So what did they accidentally detect? It was the cosmic microwave background. This radiation is the leftover heat from an early, dense state of the universe. Today, it measures about 2.725 degrees above absolute zero. That may sound cold, but it's not zero. The universe is cooling, which means it was once hotter. Far hotter. Temperature implies change over time. The cosmos evolved. And if the universe cooled down from something hotter and denser, the next question becomes unavoidable. How far back does that history go? 5. The universe had a beginning. In the 1920s, Edwin Hubble measured distant galaxies and found something shocking. Nearly all of them were moving away from us. The farther they were, the faster they receded. If you rewind cosmic expansion far enough, everything converges. The mathematics points to an early state that was incredibly hot and dense, the event we now call the Big Bang. The cosmic microwave background and the abundance of light elements both support this model. The universe has been expanding and cooling for about 13.8 billion years. Before that moment, current physics breaks down. Time itself may have originated there. Expansion once suggested a dramatic beginning. What came next was even stranger. It isn't slowing down. 4. Expansion is accelerating. After the Big Bang model gained acceptance, physicists expected gravity to gradually slow cosmic expansion. Matter attracts matter. Over billions of years, that pull should reduce the speed, perhaps even reverse it. But observations told a different story. By the late 1990s, distant supernova data revealed that expansion wasn't slowing down. When gravity pulls everything together, what is pushing the universe apart faster over time? Scientists call it dark energy. It appears to make up about 68% of the universe's total energy content. Its presence is measured through supernova distances, the cosmic microwave background, and large-scale structure. Its effects are precise, but nature is unknown. If an invisible force governs cosmic expansion, the visible universe may be only a fraction of what truly exists. 3. Dark matter dominates. When astronomers measured how fast galaxies rotate, something didn't add up. Stars near the outer edges were orbiting far too quickly. Based on visible matter alone, those galaxies should have torn themselves apart long ago. They didn't. The gravitational pull required to hold them together was far stronger than what stars, gas, and dust could provide. So where was the missing mass? The answer appears to be dark matter, a form of matter that does not emit, absorb, or reflect light. It interacts gravitationally, shaping galaxies and influencing the large-scale structure of the universe. Measurements from galaxy rotation curves, gravitational lensing, and cosmic microwave background data all point to the same conclusion. About 27% of the universe is dark matter. Ordinary matter makes up only about 5%. Basically, we are built from the minority component of reality. Dark matter explains gravity's hidden strength, yet it leads to an even more unsettling realization about what we truly perceive. 2. Most of reality is invisible. Let that sink in. Everything you have ever touched, mountains, oceans, cities, your own body, represents only a tiny fraction of what exists. All the atoms in every star and galaxy combined account for roughly 5% of the universe. So what makes up the other 95%? I already named it. Dark matter and dark energy. One provides unseen gravitational structure. The other drives cosmic acceleration. The overwhelming majority of the cosmos is invisible and poorly understood. Modern physics describes its effects with precision, yet its true nature remains unresolved. It's as if we mapped the foam on top of an ocean while knowing almost nothing about the water beneath. Human knowledge rests on a thin, visible layer. If most of the universe operates beyond direct perception, then its ultimate fate may depend on forces we barely comprehend. 1. The universe may end. The title is enough to worry everyone. If expansion continues indefinitely, what does the far future look like? The most widely supported scenario is called heat death. Over trillions upon trillions of years, stars will exhaust their nuclear fuel. New stars will stop forming, galaxies will fade into darkness, and black holes will slowly evaporate through Hawking radiation across unimaginable timescales. The universe would approach maximum entropy, cold, dilute, and silent. Another possibility depends on the nature of dark energy. If its strength increases over time, expansion could accelerate so violently that galaxies, stars, planets, and eventually atoms themselves are torn apart in a theoretical event known as the Big Rip. For now, the evidence favors gradual cooling over catastrophic tearing. Either way, the cosmos is evolving toward an end state written into its physics. So, did any of these overturn something you thought was certain? And is there a cosmic mystery we should cover next? Share your thoughts and theories in the comments. We might feature them in the next video. Also, subscribe, and share if the universe just expanded your perspective. Until our next mission, keep your eyes on the stars.
Our mission is complete, and we're coming in for landing. Stay aboard and join the crew again as we continue unveiling the stars.